So I'm now going to go on to talk about logic gates. They're the most basic digital devices, and they're called gates because they allow or block the flow of digital information, so they gate the information. A gate has one or more inputs, and they produce a binary output. So your output is always going to be 0 or 1, and it's based upon the inputs that it receives. They're formed from transistors built into chips. Every logic gate has a name and also a circuit symbol. So you need to be able to draw these circuit symbols for the gates that I'm going to go through. They have an input and an output, and the output has a function that also has a mathematical description. So you also need to be able to write what the mathematical description of the logic gates are, and you need to be able to understand their behavior, which is described in what we call a truth table or a logic table. So you need to be able to learn these. So I'm going to go through these gates now.
Okay, so this is the symbol for NOT gate, so you need to be able to draw that. It has one input and one output. We label the input A, and the output I'm going to label as Q. Now, when A comes in, what you have coming out of a NOT gate, the notation is A with a hat on, or like a line over the top. Sometimes you see this drawn as A with an apostrophe, but that's exactly the same as A with a line on. And this notation is easier when I introduce one of the rules a little bit later on. But this is your NOT gate, so you've got one input A, and coming out is your output function, which is equal to A with a line above it. And this means not A. So A, not A. If I'm to draw a truth table for this, I basically have a column for my inputs. So I have my column for my input, and I have my column for my output, which is, in this case, is equal to not A. So in this column, the only two things that I can put in are a 0 or a 1, because they're my only two possibilities. And when I draw my truth tables, I always count in order. So the lowest number always goes first and then the higher number. This is more relevant as we get bigger and bigger truth tables. So if the output is not A, well, if A is 0, then not A must be 1. And if the input is 1, not A must be 0. So basically a NOT gate is also known as an inverter because it inverts the input. So whatever you have coming in, you get the opposite coming out. That's a NOT gate. In an AND gate, you have two inputs. So I've got A and I've got B, and I've got one output Q. And A and B, the notation for A and B is you write them together, A and B. You can put a dot or you can just put them together. So it's a bit like multiplication, yeah? So A and B, you write them together. So in my truth table now, I'm going to have two inputs, A and B, and I'm going to have one output, A, B. A and B, this means. So now my possibilities for my input are 0, 0, 0, 1, 1, 0, or 1, 1. So be careful to always put this in the right order. So you're basically counting upwards. So 0, 0, here you've got a 1, here the 1 is in this column, and then both are 1s. So the order is important. Now, what do we mean by AND? Well, this means that the output is only 1. So the AND gate is only on, or 1, if A and B are both on. That's what it means by AND. So here it's definitely not on, it's not on, it's not on, and here it's on. So an AND is only gives you a 1 on the output if both A and B are also 1. And here's my OR gate. I think the name will give it away. So it's again got two inputs, A and B. Its output is Q. The symbol for an OR combination is A plus B. Okay, so my truth table, I've got my two inputs and my output, which is equal to A or B. So we write that using a plus sign. Possible inputs are as such. And the name gives it away. The OR gate is on, so it'll be 1 when A or B are on. So 0. In this case, B is on, so this will be on, this is on. And in this case, it is also a 1 because A and B are both on, so it's OR. So just a few more gates that you need to know about. You've covered NOT, AND, and OR gates. This is the symbol you've already seen for an AND gate. But if I add a circle on the end here, this means that it's become inverted. So this represents that it's inverted. And this is known as a NAND gate, an inverted AND gate. So A and B and Q coming out. So in terms of mathematical notation, Q is going to be equal to, first we AND the A and the B. So AND the A and the B are drawn together like that. And then we NAND it. So then we invert it, which means the line goes above A and B. That means that you have inverted the A and B ANDed. This is the same, right, as having an AND gate with a NOT gate afterwards. So this is known as combinational logic because we're starting to combine, but a NAND gate is essentially the same. So what that means is you can start from your inputs here, 0, 0, 0, 1, 1, 0, 1, 1. Now we can do this step by step. So the first part of the process is actually ANDing these things together. So if we AND them, we go, okay, neither are on, only one's on, only one's on. So that's our situation. And then A and B knotted, that is going to be the opposite of this because it's going to be not this. So that's going to be 1, 1, 1, 0. So this one is easy to work out. If you know how an AND gate truth table looks like, then you can invert it and then you get your NAND gate. So of course, if I move on to a NOR gate, then you know the name gives it away. NOR is going to be an inverted OR gate. So this is my symbol for an OR gate with my inputs A and B. But if it's a NOR, then it will have a circle on the end to show you that it's inverted. So that's the same as having an OR gate with a NOT afterwards. So if I look at the mathematical notation, I have my A plus B. So my output is Q. A plus B because it's A or B. And the whole thing has a line across it. Okay, so the whole thing, because you invert it afterwards, after it's been ORed. So if I again look at my truth table, first I need to know what my truth table of my OR gate looks like, and then I can invert that. Just two final types of gates to talk through. The first is an exclusive OR gate. Well, what does that mean, exclusive OR? Well, with a normal OR gate, you have Q, the output is 1 when A or B are 1. So that would give you 0, 1, 1, and 1. However, with an exclusive OR, it means that you only get the output as 1 when A or B are 1, not when they're both 1. It's exclusively if it's one or the other. So that would look like that. So that's an XOR, so an exclusive OR gate, and this is the truth table. Now, an XNOR, so an exclusive NOR gate, is basically you're knotting your XOR. So an XNOR is going to give you okay, and they're the last two gates that you need to know about.
So what do these gates look like in reality? Well, in practice, you get them on one single chip, and on one of these chips, you actually have multiple gates, but always the same type of gate on one chip. So the gates themselves are built out of transistors that are integrated onto the circuit. So you can see various different chips here, and this is something that you'll have the opportunity to use more if you take the Advanced Electronics lab.
So how exactly can transistors be used to build logic gates? Well, you know transistors can be used as switches, so let's see how we can represent these logic gates using a switch representation. So I'll start off by drawing a circuit, and I'm going to put a bulb here in the middle. Sorry, it's a bit scruffy. And here we'll have our battery. So at the moment, all the wires are connected. So this bulb is on, and on would represent 1. Now, if I draw a switch, and my switch represents my input A, and my bulb represents my output Q, when A is off, so the switch is off, then the bulb is on. But when I close the switch, then the bulb is off because you get a short circuit through here. So that's how you can represent a NOT gate, an inverted gate. What about AND? Well, if we do the same sort of thing, so I've got my power supply or my battery. Now, I've got 2 inputs, so I can have 2 switches. And then I can put my bulb over here. So A and B need to be closed in order for my bulb to turn on. And for an OR gate, for example, you can have a switch there, your bulb here, so your bulb again representing your output Q. This is going to be A, and here we can have a second switch that is B, and now if you close A or B, your bulb will turn on. So this is how you can use switches to represent our logic gates. You also need to be able to work out the algebraic function of a logic gate or logic combination from the truth table. And how you do that is you look at the outputs. So here you've got your outputs, and you look at the algebraic expressions when the output is on. So for this one, for instance, the algebraic expression for this is you have not A, because A is 0, not B, but C is 1. So you get not A, not B, and C. For this one here, where it's also on, you get not A, B, and not C, because it's a 0 here, a 1 here, and a 0 here. Then if I scoot down here, this is A is on, B is on, but C is off. And here you've got A and B and C. So for this particular truth table, Q, the output is on when you've got this situation, this one, or this one. Basically, your final expression is all of these ORed together. Okay, and what about this table? Well, here, so this time our inputs are X, Y, and Z, so they don't always have to be written A, B, and C, etc. And our output function is F. So depending on what textbook you look in or what sources, you might find them labeled slightly differently. So let's have a look at this. Well, in this case, the output is only on in this situation where X and Y and Z are both all on. So in this case, your final function is just going to be this, because you have no other states that would give you an on.